Good morning, everyone. Thank you very much for being here after tonight. We'll start right away with the first keynote of the session, Dr. Marcos Papageorgiou. Dr. Papageorgiou is author or editor of 5 books and over 400 technical papers. His research interests include automatic control and optimization theory and applications to traffic and transportation systems, water systems, and fire areas. He was editor-in-chief of Transportation Research Part C. He also served as associate editor of IEEE Control Systems Society, conference editor board of IEEE Transactions on Intelligent Transportation Systems, and other journals. He's a fellow of IEEE since 1999 and a fellow of ITSC since 2013. He received the DAAD scholarship, the Eugen Hartmann Award from the Union of German Engineers, and a Fulbright Lecturing Research Award in 1997. He was a recipient of the IEEE Intelligent Transportation Systems Society Outstanding Research Award in 2007 and of the IEEE Control Systems Society Transition to Practice Award in 2010. He was presented the title of visiting professor by the University of Belgrade in Serbia. The Dynamic Systems and Simulation Laboratory, his lab, he has been heading since 1994, received the IEEE Intelligent Transportation Systems Society ITSC Institutional Lead Award in 2011. He has been awarded also an ERC Advanced Investigator Grant. So among all of this, I have to say that he's a reference for our community. He's that kind of researcher that covers from theory to practice. I'm very glad to introduce Professor Papageorgiou.
Is this working? Yeah. Thank you, Mr. Chairman, for your nice words, and thank you also for this invitation to a highly interesting conference and the honor to present a keynote. And good morning, ladies and gentlemen, all the heroic participants of this first session after a very nice evening last night. So my presentation, as you see, is about freeway traffic management in the era of VAX, and VAX is the acronym I will be using for a variety of vehicle automation and communication systems. And as many other presentations in this conference, I will be talking about, as you see, automated vehicles, connected vehicles, things that we read even in the normal public newspapers every week, and see from a more technical point of view what it is all about in terms of traffic. So to start with, there is a well-known and infrastructure, the freeways, which were originally conceived to provide virtually unlimited mobility to road users. But like on this photograph, around the globe during the peak periods or during incidents, these high-capacity infrastructures are turned into virtual parking spaces. So since our subject is traffic management, some very quick introductory remarks about traffic management. We all know that the motorized road vehicle was a highly influential invention. And as soon as you have more than one vehicle on the road, you have traffic. And vehicles share the road infrastructure among them and also with other users, and this must be done safely. And to guarantee that this is really operated in a safe way, you need some rules, you need some regulations, you need traffic management. But this, in the early years of traffic, was static. There was no need to change with time or with traffic conditions the rules and the regulations. For example, traffic signals on the roads, they were always displaying the same duration of phases. There was no need to change whatsoever. But as the density increases, as more and more vehicles come into the roads, then traffic management has to become dynamic. dynamic, not only in the sense of different rules for different times of day, but also traffic responsive, based on current conditions, to try to adapt to the current conditions. And in fact, today we are in the era of strong congestion, and congestion is a phenomenon that degrades the infrastructure capacity, partly very strongly. And traffic management in real time needs to address this problem. No, press the wrong button. So this is an example, an illustration, in this case from the Ile-de-France network around Paris, of the situation on freeways every morning, every afternoon. Many times in case of incidents, you will see these highly expensive infrastructure being red, being congested, which means being degraded. Now, still in the introduction, just to clarify a few notions, here is a block diagram of an automatic control system. So we have a process, which in our case is the traffic flow on freeways. And this process behavior is influenced by environmental quantities like the demand, incidents, weather, etc., which influence its behavior, but they cannot be manipulated by us. So they are called disturbances in automatic control. But we also have the possibility via inputs and corresponding devices called actuators, like traffic lights, traffic signs, and so on, to influence the process so that it behaves the way we would like it to behave. Now, since we are talking about a real-time system, we need to know what is the state of the system. So we need sensors, devices, that collect appropriate information, and this information is transferred to a computing system. So you see here the separation between the real world and the computing world. And these measurements are processed. For example, you may need to estimate traffic density, which is not directly measured, or you may need to predict the evolution of traffic. And the enhanced and extended real-time information is then fed to a control strategy, and the control strategy is the brain of the system because it makes the decisions. And this whole system is run all the time in real time, this automatic control loop, at periods of, can range from seconds to minutes, depending on the specific cases. And as you see in this automatic control loop, which is essentially a real-time traffic management loop, we have technological issues like sensors, communications, computing devices, actuators. So this is a technological skeleton of the system. And we have methodological issues, essentially data processing and control strategy, which reflect the intelligence of the system, because these are the devices, these are the pieces that make decisions. Now, to summarize, in current traffic management systems, we have a process which is conventional vehicle flow. We have sensors, which are spot sensors, so look at a specific location of the infrastructure, various technologies, loops, vision, magnetometers, radars. We have communication lines, which are wired. We have computing architecture, which is usually hierarchical, can be central or decentralized in some cases. And we have actuators to influence the traffic, which are, you know, in the case of freeways, are RAM metering signals, variable speed limits, variable message signs for route guidance, and other issues. Now, as I said, we read every day in the newspapers, and of course, those of us who are more familiar, even professionally, with these systems, about evolution of new VACs. There have been significant efforts since several decades, but increasingly and more seriously in the last decade, by the automotive industry, by research community, and by government agencies to develop such VACs, which are, in the rule, usually vehicle-centric. So they don't care actually at all about traffic, they care about the vehicle itself. And the first reason for developing such systems is safety, make the system, the vehicle safer, and convenience of the passengers. So there are many systems of this kind in vehicle systems. We usually call these automated vehicles. For example, adaptive cruise control, which is already in the market, already on our roads, is one of these VACs. Of course, the Google vehicle or other automated vehicles, fully automated vehicles, are at the end of this development. But on the top of that, we also see many developments in vehicles becoming connected, meaning that they can talk to each other, can talk to the infrastructure, talk sometimes about cooperative systems. And this, in many cases, enables in-vehicle systems to become more efficient, like ACC becomes cooperative ACC, and this can have several benefits. Now, this evolution, which may soon become a revolution, changes dramatically the automatic control block diagram that I mentioned before. Because the process is, of course, still traffic flow, vehicular traffic flow, but the vehicles have now different behavior. They behave differently in the longitudinal sense, they behave differently in the lateral sense. Sensors. If vehicles are connected, they can communicate the different quantities, their speed, their position, their distance to the front vehicle, so they can become sensors, mobile sensors. Communications are likely to be wireless, but the most important thing is that we now have a plethora of new communication channels, because every vehicle can talk to the vehicle in its environment, and also to the infrastructure and vice versa. So we have many new channels of information that should be exploited for the benefit of traffic. Computing. We now have actors, vehicles, millions of those vehicles with processing capabilities and connectivity to each other, which can undertake a lot of tasks that were done previously in a control center, provided we have the corresponding, of course, strategies that are massively distributed. Actuators. If vehicles are connected, then you don't need necessarily the roadside actuators, traffic signals, variable message signs, but you can just submit to individual vehicles individual commands. And this is something that can be individual indeed. So you don't need to have just the actuator on the roadside, everybody sees the same message. You can really individually address different messages to different vehicles. So much higher granularity. All these are really revolutionary changes. They have implications for the traffic flow. The process behaves differently. And they also, most importantly, should be exploited for a better traffic flow. Now, in the newspaper, we read that automated vehicles, among many other advantages, will eliminate congestion. Is that true? Will they eliminate congestion? Well, my view, and also the view of many colleagues, is that no. And in a provocative sense, intelligent vehicles may lead to dumb traffic flow, inefficient traffic flow. Why? Many reasons. You see here just some of them. We have adaptive cruise control systems on the roads today. And as a user, as a driver, you can choose a time gap between 0.8 and 2 seconds. But the recommended value is 2 seconds. Now, 2 seconds time gap means a maximum flow of less than 1,800 vehicles per hour per lane, while today's traffic has almost 2,500 vehicles per hour per day. Dramatic decrease of the capacity. Sluggish acceleration, so that passengers do not feel badly. This means stronger capacity drop at the head of congestion. Lane changing or merge assistance or even automated systems can be very conservative for the sake of safety and convenience of the passenger. This is also a reduction of capacity. You may have dedicated lanes for platoons of vehicles, but if you have not enough vehicles to use them, then you just take out capacity for the rest of the traffic and make things worse. Lane assignment. I mean, I heard some very nice presentations, excellent presentations yesterday from different companies automotive companies about their automated vehicle and how it decides to change lanes. Okay, one vehicle changed lanes for its own convenience. But if we look at traffic, what will be the emerging lane assignment? Because capacity depends not only on how many vehicles can follow each other, but also on how they distribute over the different lanes. Nobody thinks about that because, of course, automotive industry wants to make their system convenient, safe. They don't have the view to look at the traffic implications of these things. Uncoordinated route advice, another example, and many others. So because of all these reasons, if we would have tomorrow all vehicles being Google vehicles, then it would be complete chaos. Traffic efficiency would suffer a lot. And this means that we need to do something before and in parallel to these developments at the level of traffic management so that this evolution can be smooth and can be beneficial for the traffic flow. And in that sense, we could classify the different VACs into different levels. Level 0, convenience VACs, no impact on traffic. Level 1, safety VACs, VACs that address mainly safety. They don't change the behavior of the vehicle in 99.9% of the time, just when it is needed. They have no direct impact on traffic, but they have indirect impact because if they manage to reduce incidents, then of course you reduce congestion on the roads. Level 2, the vehicle behavior is modified, but there is no button for the traffic management system to influence. And level 3, the most interesting from our point of view, the system has a traffic management button that can be addressed by traffic management in real time. So I will give you some very quick overview of the needs and some examples of things that have been done. Modeling. Why modeling? Well, these VACs are not yet there. Some are there, but just very low penetration rate. So if we want to analyze what will happen, we need to model, to simulate. But of course, models, like always, are also needed for design and testing of traffic control strategies. And as you know, models can be microscopic or macroscopic. Now, going into microscopic modeling, if you start working in this field, you would like to use a model, you will see there is no model around. I mean, now a ready model to be used. There are research tools, which are usually open source, very nice. Sometimes you may have some difficulties with documentation or the graphical user interface might not be so good. Among many examples, probably the most prominent is Sumo. We had tutorials on Tuesday here in this conference. It is a product by DLR in Germany, an expanding open source tool, not just for automated vehicles, also for conventional vehicles, but for these also. Commercial tools, commercial simulators are usually closed. Under certain conditions, the designers the companies may give you the possibility to code what you want the vehicles to do, but this is, of course, quite tedious. So in some of the simulations that you will see, we have been using Aimson commercial simulator, particularly the tool called Micro SDK. What can you do with microscopic simulation? Well, some things that have been done again and again over the years, like ACC string stability. You have a group, a string of vehicles, as we say, following each other, and then the leader decelerates, and according to the ACC parameter settings, you will see different behaviors with or without string stability and so on. Traffic efficiency, also something that has been investigated over the years with different penetration rates. So you see here different bars for different penetration rates. Here you see the capacity of a lane in vehicles per hour. And in different values here, the x-axis are different time gaps. So if the time gap is 1.1 second, you see here for any penetration, capacity remains the same because 1.1 is about the time gap also of human drivers. But as the time gap increases, you see that the capacity decreases quite strongly at 2 seconds. with ACC vehicles and 100% penetration for the reasons that I mentioned before. Of course, you have the option also in the other way to go down to smaller time gaps, and then you can really increase the capacity. Macroscopic modeling. Well, things there are even worse. There are very, very few works on macroscopic traffic flow modeling with VACs. Usually, there are gas kinetic developments applied. You start from individual behavior and generalize to the macroscopic level. And there are many difficulties how you validate these models using microscopic simulation. You may need to have different penetration rates. You may need to have multi-lane traffic, because now the VACs allow you to also influence as an actuator the lane change behavior of vehicles, and then you should also be able to model. These are things that you can do as an example with macroscopic simulation. So for example, here we have the case of conventional vehicles at a stretch of freeway. This is the density here, stretch of freeway over time, and there is an on-ramp here, so you have the creation of congestion. You may have traffic instability. Then if you use the model under different parameterization with ACC vehicles with specific parameters for ACC behavior, you may get a more stable traffic, as you see here, if the ACC is string stable. And then if you use CACC and you are able to also increase capacity, you see that you can not only stabilize traffic, but you can also avoid congestion. Second theme, monitoring estimation. The point is here that usually for traffic control, we need to know traffic density, but traffic density is very difficult to measure, and this is the reason why we have in conventional traffic many detectors, loops, or whatever on the road. But now with connected vehicles, as we said, we have abundantly many new real-time information from connected vehicles. So we could use that instead of sensors. Of course, as long as traffic is mixed, comprises both connected and non-connected vehicles, this information will not be complete. And that means that you probably need to still have some roadside detectors, and you have to design fusion techniques for conventional and connected vehicle data in the aim of reducing more and more the need for roadside detectors, and eventually even replace it. So here is just an example of a system out of many that have been developed. You see here the real freeway with arbitrarily long segments, traffic variables that we would like to estimate, in particular the densities, and can design a Kalman filter for estimation of the densities, which is fed by what? For example, there is a paper tomorrow on this system by the speed of connected vehicles that is conveyed to the control center, plus a minimum number of flow measurements from conventional loops. And this becomes then an observable system that can indeed estimate density. You see here a case study where we consider data, conventional data from a 10-kilometer long freeway from the Netherlands, and we emulate using these measurements the information from connected vehicles, and then we can estimate, as you see here over time, the density quite accurately, and even on-ramp or off-ramp flows that are not measured can be estimated by the scheme. And so we reach the third and probably most important theme, which is traffic control. Questions here are, which conventional traffic control measures can be taken over from today's situation and in what form? But most importantly, which new opportunities arise for more efficient traffic control? And here we can distinguish between three levels: vehicle level, local control level, and link or network control tasks. So vehicle level, as we said, if every vehicle tomorrow would be a Google vehicle, we would have cars for reasons that we mentioned. So the point is, how could we possibly change in real time and at specific locations where it is needed, some parameters of these systems, for example, the time gap of ACC or the acceleration rate of ACC systems, not all the time, just few percentage of the, like 5% of situations when this vehicle goes through a bottleneck at critical traffic conditions, we would like to change some characteristics in order to, to increase capacity or decrease capacity drop. So that would be vehicle level control, the possibility to directly influence some parameters of VACs that are included in the vehicle. Local tasks. There are several examples of tasks. This is one, for example, merging of vehicles on a freeway. What we want is the vehicles, of course, to merge safely and conveniently, but from traffic point of view, we also would like to have maximum throughput. Specifically, this means we need to specify the merging sequence and the vehicle trajectories so that we guarantee best performance for these criteria. And important questions here are whether vehicles cooperate, they can talk to each other or not, whether there is mixed traffic or just connected vehicles, and so on. Another example, local task example, bottleneck control. You see here again a freeway, a bottleneck area due to the non-ramp. We know that if the bottleneck area saturates, if it's activated, then we have capacity drop, infrastructure degradation. So I would like to apply speed limits, speed control over the vehicles upstream of the bottleneck so that they are released here at the capacity. This corresponds to a sort of mainstream metering and aims at mitigating the capacity drop. Can be done with conventional variable speed limits, but even better with connected cars. Here is an example, again, from simulation, freeway from Perth in Australia, and simulated but validated model, real situation, space over time, red is low speed. You see here clear bottlenecks that are there and are activated without control. Then if you apply conventional, in this case, variable speed limit control, you can maximize the throughput here and mitigate the congestion. Link level control. Well, we have different control actuators, as we mentioned before. So on a link of few kilometers, you may, for example, have RAM metering, which can be conventionally implemented or with connected vehicles. But as we said, you can influence also the lane changing behavior of connected vehicles. And you can also control the speed of the vehicles. So how can you apply all these control measures simultaneously in a synergistic way so that you optimize traffic flow with the combined action of all? This is something that can be cast in an optimization problem. You see here again an example of application, this time Monash Freeway from Melbourne, Australia. 4 lanes, many on-ramps, off-ramps, and a few bottlenecks for various reasons. And then applying such an optimization scheme, in principle, you can get sensible improvements. Here we see the situation of speed over space and time over lane, because now you can also influence individual lanes, so you need to look at individual lanes. Also, not just the whole of traffic. So we have lane 1, lane 2, lane 3, lane 4 without control. And then by applying in an optimal way a combination of these 3 control actuators, you can end up really with a virtually congestion-free traffic flow. I will conclude with some thoughts about functional and physical architecture. So in today's system, usually you have a hierarchical traffic management architecture. You have the freeway, you have some roadside controllers near the freeway, and then you have the traffic control center, which essentially makes most of the decisions. There may be some different share of tasks between the two, but this is usually what you encounter in conventional traffic control centers. But now in the future, things, as we said, become different because every vehicle is a processor that communicates with other processors. We have a huge multi-processing system. So there is a vision of some people that the system could be completely decentralized. Some people think you don't even need a control center. And this is something that we know, of course, from nature. If you have a fish flock or a bird flock, right? A bird flock moves as a unit, but there is no central control. There is no coordinator. Every individual in the flock just measures distance and other things from the neighbors and behaves according to certain rules. And these individual rules emerge into macroscopic moving of the flock in an efficient way. Can we do that with cars? I don't know. Maybe. But we don't really have mathematical tools that would allow us with specific purpose to start with microscopic and end up with a desirable macroscopic behavior. So it may or may not be possible. Nature is, of course, much more wise because it had a lot of millions of years of time to reach that situation, but I'm not sure we have so much time. So if every vehicle would be an individual, autonomous, automated vehicle based on its sensors, I don't know whether this could be still moving or be designed to move in a way that is beneficial not only for the vehicle but also for the traffic. Of course, things can become a bit better if you have V2V communication, still a decentralized system, but now every vehicle can get a lot of information from several hundred meters upstream, downstream, whatever is needed through the communication. So, of course, there are many questions. How far ahead or behind should the vehicle be able to see in order to act in a way that is sensible, not just for itself, but for the traffic flow? Where should data aggregation take place? Should every vehicle really be a small control center? Or how should it work? How to deal with mixed traffic if you have vehicles that are not connected? What about roadside actuators? Should they remain or should they be removed? So these are all important questions, but the most important one is how would such an intelligent control strategy look like that would be distributed over all vehicles without anything above it and would still result in an efficient traffic flow? That's a very open question, and it's open even whether we can reach that at any time. And of course, another question is, what about network level traffic management, where you really need to know the network situation in order to make route guidance or RAM metering in some case. So a more probable development will be hierarchical traffic management, where you have different levels, as you see. So at vehicle level, you have ACC, obstacle avoidance, lane keeping. At V2V level, you have CACC, cooperative lane changing, cooperative merging, warning alarms, platoon operations. And at each infrastructure control level, you may have different things like speed of vehicles, lane changing, headways, platoon size, RAM metering, and route guidance. And this could even be decomposed a little bit in order to reduce complexity so that you have network traffic control and link traffic control. We reach the conclusions, make it short. As said, intelligent vehicles may lead to dumb traffic flow if not appropriately managed. This means that all these important developments in the direction of VACs by automotive industry and research must be accompanied by corresponding traffic management developments so as to have maximum synergy, because what we want to have finally is not just to sell more cars or to have more profit for the automotive industry, but we want also the society to gain from these developments, and that means more efficient traffic flow. So traffic management remains vital while VACs are emerging, and automated vehicles will not automatically eliminate congestion. Thank you very much.
Thank you very much, Professor. Very, very challenging. Is there any question in the room? We have time for one or two.
Thank you for this excellent talk. With regards to
wait a second.
Thank you for this excellent talk. It's very interesting. With respect to the deployment of automated vehicles, there are two other major issues that might be interesting to be considered. One is the multimodal interactions between the individual automated vehicles and public transportations. I think one way of using efficiently the automated vehicles or the VACs would be to cover the needs for the last mile or the last kilometers between the individuals and public transportation transition points or boarding points. The second issue I wanted to mention is the business models. Right now with the OEMs, the car manufacturers, we assume that the traditional business model of people buying cars will go on forever. And if you look in the States, for example, average family have 2 to 3 vehicles, which is kind of, doesn't make sense, right? And I think that the deployment of automated vehicles may in fact reduce the number of vehicles on the road if we change completely the business model and going from an ownership business model to rather a service business model like in telecommunications. Today, the smartphones are given away. What you pay for are the services and the bit transfer rates, etc., and the use of the bandwidth. And in a similar way, we could consider that the automated vehicles will be used and we will pay per kilometers driven between the individual position and the public transportation boarding points. So I think if we consider also the change of business models, that may have a significant impact in traffic management. And I wanted to have your view on that, if it's possible.
Thank you very much for these contributions. These are extremely interesting and important questions. The first one, last mile, yes, for sure, automatic vehicles can help a lot in that sense. There are also other models or other thoughts about how they could be used. I suppose life will show at the time automatic vehicles will be a reality, what exactly will happen. It might reduce the demand, as you say. Whatever I said is everything else being equal. So if we have the same traffic demand, what will happen? There are reasons why demand on the roads could be lower. There are reasons that it could increase. I must say this is not my topic. I try to learn from colleagues who work on these very important issues, trying to predict what will happen. Now, regarding business models, again, this is something that the automotive industry and the consumers will decide. It's hard to predict what will happen. We know that there are some companies like Toyota or Volkswagen which say you will never go into automated vehicles. People will always like to drive themselves. There are others like Audi, BMW, of course, all the Google and so on, which are really heading for automated vehicles. It's very hard to predict what will happen. From my little point of view of traffic management, all I say is that we should be prepared for whatever evolution so that whatever happens efficiently at the level of traffic flow and not just at the level of the individual automotive manufacturer or individual user and so on. That's the message.
Thank you very much, Professor. Well, we have a little gift for our keynotes to thank them for the contributions. I'm going to give him now.
Yes, this gives me the opportunity to introduce our next keynote speaker. Next keynote speaker will be Herman Winner, and we are proud in our society to connect industry and academia. And Herman Winner himself is one very good example because he did that in one person. After he received his PhD in physics, he joined Robert Bosch in Germany in 1987, and there he started in the Prometheus program, which, as you might know, has been the European highway automation and intelligent vehicles program. After that, he became responsible for bringing ACC and by-wire systems into the market, and he did that successfully around the turn of the century, I believe. So he can rightfully be recognized as one of the pioneers of ACC from an industrial perspective. And today, since 2002, he's full professor at the Technical University of Darmstadt, of course, looking at automotive technology. And 2012, he has been awarded with the Institutional Lead Award for this. And his talk will be about the approval trap and how to avoid it. I'm very interested to see what you have to say to that.
Thank you, Christoph, for the nice introduction. Good morning, ladies and gentlemen. I will give a talk how to address. I'm not sure that we can avoid, but we will see at the end of this presentation. What is an approval trap? Let me introduce something. Just a mental experiment. You just think some years or decades far from now that the development of an autonomous driving vehicle has finished. And then you will say, okay, let's go to the market. And of course, there's a prerequisite to say the risk of autonomous driving should not exceed the risk of conventional driving. I think it's normal common sense to do this. But then we come into some trouble. We have to get a kind of approval that this requirement is fulfilled. So we can develop, perhaps we can also produce on the risk of the manufacturer, but for the usage, we have to have an approval. And for this, a validation process for that risk estimation. Let's have a look into statistics. German statistics, doesn't matter, I think it's not so far from the Spain statistic yesterday, the keynote, and we have a lot of mileage, and we can then count the number of accidents with personal injuries or fatalities, and then you can calculate the average distance between two accidents of a given category. Perhaps just all accidents, it's about 340,000, and on autobahns, nearly 2 million. Looking for personal injury, it increases by order of magnitude, both cases. And if you look for fatalities, you have 200 million or 660 million kilometers between two fatalities. And this big number is on one side very good because it shows that there's a high level of safety. On the other hand, this is a risk reference. Not to have more accidents and categories of personal injuries and fatalities with this number. How can we come to a way to do this? And just to make it more clear, to compare to lifetimes of human. If one person have about 55 years license and practice driving with approximately 14,000 kilometers per year, which is average for Germany, we have a lifetime mileage of 770 1,000 kilometers and about 15,000 hours for driving this. So if you look for this number, the lowest number, the registered accidents of 340 kilometers each, and a self-causation rate of about 60%, and the same for the average of fatalities, you can count that you have an average in life 1.4 accidents caused by you. So we have always to see all the situations you have in one life, in your experience, have to be a kind of reference for an autonomous driving vehicle. But if you look for the fatality rate, it should take 450 lifetimes of experience that there shouldn't be any accident with fatalities by an autonomous system. So the conclusion first is, we know the driver makes a lot of mistakes, but only few of them leads to a consequence with injuries or fatalities. And that's a good way, but it's not easy to look for machines to do it in the same way. Conventional ADAS, the ones driver assistance systems, will be tested with different tools, but the major part is to have a kind of endurance driver test. The word is not always clear. It means also customer close behavior driving systems. Then you have to see what occurs on 1 to 10 billion, what is now about state of the art. But the main point is, today ADAS, we have the driver, and so the design is more for controllability, not for safety of the system in all situations. The driver will supervise. So then we can see what should be, if you take the same strategy, what have to take for travel distances for autonomous driving. Can make some kind of statistics. I think it's not bad to start with Poisson distribution, because an accident with this low rate is similar to the independently occurrence of this. And let us assume we have a value where 2 events or accidents will occur with the driver, and we say the autonomous will be twice better. And then you can look how often you will get in this distance 0 events, 1, 2, or 3, or 4 events. And if you look for 0, 1, or 2, it is not really, you cannot differentiate between them. There's a higher probability if you have 0 that it is for the first time, for the first case, but it could also occur with a given probability for the second case. So you need a higher number of expected values to differentiate expected values from one group to the other one. For that you can compute a distance factor. That means how bigger must be the mileage compared to the reference mileage. If you just select that there is no event, it should be 3 times more. If you have about 4 or 5, it should be nearly 10 times more. Then you can differentiate on a level of 95% confidence or an error level of 5%. But if you have a system which is similar, same expected value, then you will not reach with a high probability this stage. Because it's also like the error probability, its occurrence will be about 5%. If you will look a reasonable figure with 50% success, then you need another factor, the performance factor. You have to be better in order to reach this distance factor. The best distance factor is 3, and you need a system which has to be more than factor 4 better than the reference level in order to have this with 50% chance. If you have just twice better, you have to take about 10 times more. So all the figures given in the statistics on mileage per accident, you have to factorize with this distance factor, and I think it is realistic to have about a factor of 10. Oh, this is, forgot the animation. And if you look for this, the lowest figure is about 100 million kilometers, but you can also generate figures with fatalities on perhaps autobahns or motorways to come to 10 billion kilometers. For that reason, you say Google did a lot of work, great work, but they are just marginal compared to this level of needed mileage. But then you can discuss with some other engineers for safety certification, and they always told, no, we didn't such thinking for the conventional system, like today vehicle systems, ESP and so on, and we don't do this for aircraft. If you will make the same figures for aircraft, you come to trillions and so on. So there's must be a fundamental difference if this is true. And let's check. There is a basic difference. We have a very good knowledge on the screen part of the vehicle. We know all how a failure may occur, all the different reasons for this, perhaps by corrosion or temperature change or load. And for this, we have always tests to estimate the effect on the lifetime. And we have very good processes now for electronics with the ISO 26262. But we do not have any strategy how to certify safety of an intelligent system. With the basic the models of Rasmussen and Donges to just give them only blocks for beating, but there's no really a model behind to predict something and to certify safety. So that's the reason we have a very big lack of information. And if you look on an approval, you would see that you can develop a lot, but then you come to the point where you have to stop. That's the approval trap. And then we can perhaps analyze what is missing in order to bridge the trap. If we will not stop the direction of autonomous vehicle, and I think nobody here in this auditorium will do this. So we have a lot of question marks. We do not know currently worst case test cases. We do not have metrics for identification of criticality of situations. The environmental influence on perception is not always clear. And how can we test behavior to be a high robustness and safety? And if we use simulation methods, which is typical with model in the loop, software in the loop, hardware or vehicle in the loop, yes, we need this, that's obvious, but how can we say that this is valid? And up to now, there's no idea to validate. And then we have to look for our methodology. Do we have the representative cases what is necessary for an approval purpose? All these question marks has to be responded and to be clarified. And the question is, how can we come to this situation to gain the missing knowledge? One important point will be the evolution, so all the things in between. Two ways of evolution, in my point of view, you can see. One is that what it was expected 5 years ago, when you always look just on the roadmaps of the car manufacturers, they will make a functional evolution. They have predecessor functions, and with the predecessor functions, you get a lot of databases, information about situations, specific road parts of problems, and you can collect sensor raw signals. You can establish for that test cases, for real and for virtual tests. You can do this on a virtual assessment of automation and field operation in such a way that you have in mind, it means processed but not with an actuator, and the new function, and then can assess if the behavior is okay. And you can make the simulation more and more realistic, and you also can collect statistical data for risk assessment. This will be always very helpful to generators. So then we have just to look, what is the evolution path? But if you look for the possibility of autonomous driving, you will find not one. You can generate thousands, 1,000 types of autonomous driving. So it was not clear from which side we will come. And one way is the evolution triangle, to start from 3 corners. One corner is always in mind, then we come from simple scenarios, car following, just lane keeping, perhaps a little bit lane changing, and make this more and more to go into the highway pilot. Of course, you start with a simple scenario. Another simple point is the low speed, because a low speed has advantage. There's always a simple fail-safe state, just stop. And then we can make an evolution coming from the speed, from parking to autonomous valet parking, and combine something in congestion assistance. And the first one was full speed range ACC. And the third one is coming from the high risk. High risk in that case has a big advantage, that it's easier for a machine to decide this situation is more dangerous without an interaction as with an action. And this is being done with collision mitigation brake, collision avoidance brake, perhaps collision avoidance evasion, and coming to the last one, an emergency assist. If there is a heart attack of the driver, that the car will drive to a fail-safe state. And this is also a very big part for the general evolution, because if you can do this, then you have also the fail-safe state for the scenario at the top. So for this, you will find like a color triangle that you need for white, as well red, blue, and green. And today we are really here, and then we have to come closer to the center. But it makes clear it's not so easy to find a predecessor-successor system. Another way is what I called here use case extension. So we will not make gradually stepwise automation. We will start with full automation, but just for a limited area. Just few roads and more roads. And there's a big advantage to start with this. We do not have statistical data which we can compare. So it must be just safe for this first part of the use case. And later we get more and more field experience and makes the system more and more mature. And this can be always combined with a supervision system by a provider and could be controlled in case of safety problems on given parts that they will shut down their function. The Google approach, especially with a small car, is similar to that way. If you make a comparison between, you will see the difference. Here we have the full operation area, but not full functionality. Then you have the full functionality, but the operation area is first limited. And you do not have such an approval trap, because you have to just approve on an absolute value of safety or an own criteria. It's not a criteria of 100 millions or billions of kilometers. For approval, you can say you will use some virtual techniques of simulation. Yes, you can do, and you can do a lot in between real driving and software in the loop. In general, there's a big potential, but you have always a problem of validity. The virtual approval could be part from the idea running the tests so that you come to similar travel distances in the computer. If you will do this in real time, you have to see, in principle, this is about 2,300 years. So if you will do this in 1 year, you need just 2,300 computers or systems can do this in real time. It is not cheap, but much cheaper than to do this with 1 billion kilometers. 1 billion test kilometer typically has to be factorized by 3 or 5 euros per each test kilometer. So you can see the invest of test kilometers and look for this one. Then you need just validated models, component models. You can check first the validity with component testing systems, environment conditions. You have to derive from test drives, and the vehicle dynamics is the lowest problem because you always can do this with test maneuvers as is state of the art. The situation creation is a little bit more critical task I will show later. You can do this by permutation principle or by stochastics like Monte Carlo approaches. Unsolved now is how to validate behavioral models of other traffic participants. That's a big point to see how can we all the behavior variants, which are also not from the subjects different, it's also intra-individual. Perhaps the behavior this morning after the event yesterday might be different to the behavior when you have a sleep with 8 hours. So we have to take into account, and we do not have clear figures about this. But situation generation is not easy. You will find a lot of sceneries, static and circumstances, and you can make many constellations of traffic partners. So if you just look for the simple lane change maneuver to the left or the right, you have in principle to take 24 vehicles which could be relevant for a given situation. And they can have always different speeds and different behavior, decelerate, accelerate, change, and so on. So you come in a very high permutation problem. And it will overload any computer cluster you can imagine. It's very easy to calculate this. One problem is, for the evaluation, you first just start, it will occur a virtual accident and just counting them compared to the accident in real life. But that's a big problem. And there, the question, how can we come to another approach to avoid the permutation just counting virtual accidents? One way could be to decompose the task of automation. There's a scheme used from GRAB coming from analysis of accidents. And they could say, if there is an accident, at least at one layer of this, some mistake was done. So if we can generate safety on this layer with given criteria, we have the chance to avoid the full permutation problem, and we can make permutations more in one layer and combinations of this. This gives you hope that you first can modularize the tests. If the test and the architecture is compatible, then we have a very good chance to reduce and reuse the test results. And in general, we can always look for each layer, what is the worst case combination or worst case part, and there's no need to combine less critical parts of this for the given situation with the other layers. So you can find out the redundant test and can delete it from your test catalog. But you need new criteria for pass-fail on the decomposing layer. A matrix for this, which is now not available. If we can do this with a matrix, there is some hope to find a performance comparison between human and machine, and we don't have this always with the accident number. But it's an open promise, don't know. General, the virtual approval has a big chance, but we have to find if the test case catalog of this one will be representative. A minimum set is just to check the given reconstructed accidents, which should be always part of this. So you can take GIDAs or other technology to see if this is done. But it will not help too much because nobody knows about the different behavior perhaps of humans react on autonomous driving, because autonomous driving will not a pure copy of human driving, because then we cannot get the safety level. So general simulation will be important, but it will not work in the beginning. That's the point. You need, for beginning, some other strategy. But you should always look to build up the capability to do this. So we have to find a little bit other words. Next point was to say worst case testing. Principal idea is if we have all the critical situations and we can see the system will handle these, so less critical situation will be handled too. If we have a clear criticality matrix, then we can really do this. But there's the same, we have a problem with matrix. Even only checking a critical situation, we have to look for a high variety. So it's not a short number of the worst case tests. And even in this, it is a big challenge. You can see, perhaps for time reason, I will come a little bit further with this. The driving test still is a very good basis in order to get real knowledge. But it will change the character. It's not more to say with 10 or 100 million kilometers, there were very few accidents. No, the information is better to always collect the data from the real situations and to look, do we have this the same way in the computer for modeling and for test cases? Do we have the same behavior models on this? And we have also, is our test catalog always filled by the right test cases? We can make a priority on this test cases, about the worst case testing, and we have to look for a completeness. And only through the real drives will help us to come to the validity and the completeness of test catalog. And if you make, again, statistics, you maybe make a carefully estimation. If you look on the surprising events, surprising means it was not stored in your database and it was relevant. Then you will find, first, you will find a lot you haven't model in your model library. But after some mileages, thousands here, you will have less and you will count just very few, and then you can make a trend line, and then you can extrapolate how many surprises you can expect it. And then to see that say you have a catalog quality of 99.9% completeness of test catalog and simulation models. So you can use it to make a quality identity. Then, if you put all things together, the matrix, stepwise evolution, and virtual approval, it should sufficient to bridge the approval trap. This was in former presentations, one of the last slide. But after some thinking more about, we will have always some uncertainty if we do not have the validity for all the points. So we have a kind of chicken egg problem. We need data from the field in the market to have the validity for the alternative strategy. So we have perhaps an approval trap filled up with something, but will not really be sufficient. And so we have to look if there's an alternative way. And one is to say the introduction should be done risk limited. What does it mean? Let's first make a test drive, 1 million kilometers, 10 million kilometers. What is feasible? Then we get an expected value, then we get a value about accidents of the different categories. And then we can calculate from this one a worst and a best case factor where the expected value should be framed in. Then you take the first case factor on the safe side. You can calculate the maximum expected risk for a given number of autonomous vehicles in the field. And if this risk, this worst case risk, is below a kind of a detection limit on the societal point and the statistical point, so that you will come to a kind of acceptance of this, then you can calculate how many cars you should introduce in a given phase. And then you can do this recursively using the travel distance from the new car in the field, again, a statistical basic in such a way that you can introduce new cars. We made some calculation on this. It's really on the limit. You will find cases and assumptions that it will not, it's a kind of exponentially grows, but exponentially grows in two ways. One way is in that way, hopefully. The other way is just going down and totally have a cumulative maximum number. I'm optimistic that the first can occur, but it's really at the limit. With such a strategy, we can for the first time come to a little bit different. We just skip the approval trap for the first time and then get the matrix. So we conclude. Currently, the approval trap is still existing. We have different promising approaches to overcome this trap, but the prerequisites for this are not state-of-the-art and really far from state-of-the-art to come to validity and completeness. Functional evolution or use case extension are strategies to get sufficient data, but there's always some doubts about the validation, and you have to see that the test drives will play for the first time the key role for the risk assessment and the methodological work for the alternatives. And the risk limitation risk introduction strategy might be a chance to tunnel the barrier or to skip the trap for the first systems. So that's the end of my presentation, and thank you for your attention.
You have time for a question? Okay, so let's go to that.
Very nice.
There's a microphone coming.
Thank you. Very nice presentation. Thank you. The question I have, as a human being, at least in America, you start getting to drive around 16 years old. And so you gain experience. So your first 5 years, you have a higher percentage of getting into accident than, the last, let's say, 5 years. Or no, as you get older, you have probably higher chance. But anyway, so you don't have that uniform distribution on it. We think we understand the human driving behavior, given that we've been doing so much research for the last so many years. And we think that if every car on the road is autonomous, we don't have a problem at all. But if you take the human being as they get experience in driving and get the model for the autonomous vehicle that has experience already based on simulation and others, then now the problem is checking out where you have autonomous and human at the same time, driving on the same road. So how would the experience matter? Is it okay if we agree that we're going to have accidents, because we do every day, with autonomous vehicles, and we should not make a fuss about it? It's just we try to design it in a way that it can maybe limit the injuries or limit the fatalities and so on, but accept the fact there could be autonomous vehicle involved in an accident. So how do you see that?
There are two domains of thinking. If you think on the more philosophical way and looking more for societal reasons, it's hard to accept that automated vehicles will make accidents. But from a technical point of view, with this high number of situations you cannot really fully avoid. You have some situations where a computer does this 10 times better than a human, but at one time it will occur. So in general, for society, it will be better if we have just the 1 compared to 10, but we have still to say there is a risk like other technical systems. And the expected value for all stakeholders should be better than the figure with human driven cars.
I'm very sorry, we have to move on. We have a strict general chair. He wants to have the conference on time, but Herman will be there in the coffee break and in the lunch break, so I recommend you just grab him. I just want to thank him for his presentation and give a little present.
Thank you very much.
Can our yesterday's keynote, Nobe-san and Professor Crane come to stage to give them their awards as well, their gifts? Yeah, also here.